For centuries, astronomy has been humanity's window into the unknown. From the time ancient civilizations looked up at the stars with naked eyes to the age of modern space telescopes like Hubble and James Webb, we've been pushing the boundaries of what we can see, measure, and understand. Every time our tools evolved, the universe revealed something new. Galaxies billions of light-years away, black holes swallowing light itself, and cosmic radiation left over from the birth of time. But now, it seems we've reached a strange, sobering moment in our journey through the cosmos. We may have hit a limit in astronomy. What does that mean? It doesn't mean we've stopped discovering things. Quite the opposite. We're learning more about the universe every day, but our discoveries are starting to outpace our ability to observe and verify them. There are fundamental barriers, physical, technological, and even cosmic, that prevent us from seeing any further. In simple terms, we've reached the edge of what's observable. Let's start with the most literal boundary, the cosmic horizon. According to current cosmology, the universe is about 13.8 billion years old. Because light travels at a finite speed, roughly 300,000 kilometers per second, there's a limit to how far back we can see. That limit defines what astronomers call the observable universe. Beyond roughly 46 billion light-years in any direction, light hasn't had enough time to reach us since the Big Bang. That means there are likely regions of the universe we'll never see, no matter how powerful our telescopes become. It's not a problem of technology, it's a problem of physics. The speed of light is a cosmic speed limit, and the universe itself is expanding faster than that light can reach us. Even within that observable sphere, there's another wall, the surface of last scattering, also known as the cosmic microwave background, CMB. This faint glow, detected in every direction, is the oldest light we can see, released about 380,000 years after the Big Bang, when the universe finally cooled enough for atoms to form. Before that, space was an opaque plasma of electrons and protons that scattered photons constantly. In other words, we can't directly see earlier than that moment because light itself couldn't travel freely yet. The CMB is like a cosmic fog. We can sense what's behind it through theory and indirect effects, but we can't look beyond it. It's the universe's final photographic limit, but the barriers don't stop there. Even within the parts of the universe we can see, there are forces and conditions that make observation nearly impossible. Take black holes, for example, regions where gravity is so strong that not even light can escape. They represent a literal boundary of observation. We can only infer what happens inside their event horizons from their gravitational pull, from jets of energy escaping their edges, or from simulations based on Einstein's equations. The Event Horizon Telescope gave us humanity's first image of a black hole, but it wasn't a photo in the traditional sense. It was a map of radio emissions, pieced together using algorithms and data from around the world. Even with that, what lies beyond the event horizon remains unknowable. Then there are dark matter and dark energy, two of the most profound mysteries in physics. Together they make up about 95% of the universe, yet we can't see or directly detect either of them. We know dark matter exists because its gravity bends light from distant galaxies, and dark energy because the universe's expansion is accelerating. But beyond those indirect clues, they're invisible. No telescope, no sensor, no detector has captured them directly. We're staring into the dark, trying to describe what we can't touch. In a sense, that's another limit. Not of curiosity, but of method. The tools we have were built to detect light, and most of the universe doesn't even use it. Even our most advanced telescopes face physical constraints. The James Webb Space Telescope, JWST for instance, can peer deeper into the past than any other instrument, observing galaxies that formed just a few 100 million years after the Big Bang. But even JWST can't see infinitely far. Infrared light, which Webb relies on, gets stretched and absorbed by dust, cosmic radiation, and the expansion of space itself. At some point, the ancient light becomes too faint, too redshifted, too diffuse to detect. It's like trying to read a book where the ink fades the further down the page you go. There are also technological limits. Every telescope, no matter how advanced, has a resolution cap determined by its size and wavelength. To see finer details, we'd need mirrors the size of cities, or space-based arrays spanning thousands of kilometers. That's not impossible, but it's far beyond what we can currently build or launch. We're also running into practical limits. The further we go, the more data we gather, and the harder it becomes to store, process, and interpret it all. We're now drowning in cosmic data faster than we can understand it. And beyond all that lies a philosophical boundary, the limits of human comprehension. The universe operates on scales of distance, time, and energy that defy intuition. We can describe them mathematically, but we can't really imagine them. When we talk about the first trillionth of a second after the Big Bang, or about multiverses branching beyond our cosmos, we're reaching into realms that may never be testable. Theoretical physics can go where observation can't, but without evidence we can't know if we're right. In that sense, astronomy may be approaching its metaphysical frontier, where science meets speculation. Still, hitting a limit doesn't mean the end of progress. Every time humanity has faced a boundary, we've found new ways to push past it. When our eyes couldn't see further, we built telescopes. When telescopes couldn't reach space, we launched satellites. When visible light wasn't enough, we turned to radio, X-rays, gamma rays, and infrared. Now, we're entering the age of gravitational wave astronomy, detecting ripples in space-time caused by colliding black holes and neutron stars. This is an entirely new way of seeing the universe, not with light, but with gravity itself. The same may happen with neutrino astronomy or quantum communication across cosmic distances. The truth is, the universe will always stay one step ahead of us. There will always be mysteries we can't yet reach, signals we can't yet decode, horizons we can't yet cross. But that's the beauty of astronomy. It's not about finishing the journey, it's about continuing it. We may have hit a limit in what we can see, but not in what we can imagine. And imagination, after all, has always been humanity's greatest telescope. So yes, maybe we've hit a limit, but it's only temporary. The edge of knowledge is never a wall, it's a doorway, waiting for the next generation of dreamers to open.